on the other hand, in performance and load testing, you're actually trying to simulate effects like Mother's Day load or other critical events where you have lots of parallel sessions open at the same time. That's not the goal in our study. Our study was trying to see how many fast test cases you can execute per second using tight loops in each test generator, and also due to running several test generators in parallel. If you want to play with traditional performance testing aspects, you can add, and you can use our GUI to add delays in between the test cases, and then of course you can add more parallelism into the tests, because the machine resources like CPU and memory and all that then is split between the generation threads much more evenly. So if we look at how Defense6 is built and what enables us to run our test cases that fast, one of the key attributes to our tools is that we are not bound to any single hardware platform. So for example, some of the tests I've been doing myself is on a very low-end Macintosh, Apple environment, so the operating system constraints and the hardware constraints are very loose. Obviously, we don't support Mac, but of course, that doesn't stop you from trying out different operating systems as well. The capability of running parallel processes and threads has always been built into our tools. So when you look at a tool, individual tool, that how you probably have run our tools in the past, we have the architecture in our tool is divided so that you have a single thread dedicated for the test generation and anomalization. And so the more processes you have in parallel, the more test generators you have in parallel. And then each one of those test drivers, which is actually executing those protocol sequences and those test cases, is also dedicated into their own drivers. So the more threads you enable in the tool, the more protocol sequences you can handle in each one of these test generators. So combining these, running tools in parallel, running the actual suite of tools in parallel, and then combining the multi-threaded capability enables you to run more test cases and consuming all of the hardware resources on your test platform in much more effective way. There's of course a lot of bottlenecks also in high performance testing. So the first bottleneck that almost always comes is with the network bandwidth. So unless you have high performance network interface cards when you or optical, or if you are restricted to wireless, then you can do less test cases on one single platform. But you can then divide the test generation between different, even like virtual hosts or physical computers that actually generate a test case, and then divide the test generation between those. And that will enable you to go around the restrictions of the operating system network sockets and the actual physical restrictions of the network interface cards. Especially if you are using our tools on laptops or mobile devices, then the CPU and memory are, of course, quite often the first bottlenecks. So like in the examples I will be showing on a low-end dual-core computer, the CPU often becomes the first bottleneck. So the test generation process and also the test drivers still spend quite a lot of CPU cycles on each one of those test cases. Again, going back into the traditional performance testing, you wouldn't use that much CPU power in traditional performance testing because each one of those test cases is exactly the same. There's very little change in traditional performance testing, but in fuzzing, every single test case is different from each other. So we need to recreate those test cases in between every test case, and that actually can create a lot of CPU usage. And if we look at the architecture, of course, when you use multi-threaded execution, the entire process uses one single memory space. But if you use parallel processes, then the memory usage actually can also become a bottleneck of the test execution. But of course, if you look at performance fuzzing, parallel fuzzing, one of the most interesting metrics is if you actually can find any new problems with that. So you always have to think back to the main purpose of fuzzing, and that is how many bugs you actually find. And interestingly, you can actually find interesting new anomalies in the target system as well. So, for example, this example shows a very old example actually shows that an individual test case, when you run a typical like valid requests at a specified load against the system, you don't necessarily always consume that much power from the target system. But then suddenly when you have anomalies in the traffic, each one of those test cases can take tens or hundreds of times more CPU cycles from the test target. So planning your high-performance testing can actually reveal a completely new set of issues in your performance-critical services and devices as well. So don't hesitate to contact us if you have any questions on this topic. In our tests, we used Dell hardware, but any off-the-shelf hardware should be fine. The only reason we chose this one was that it actually was easily available and price effective, and also because the amount of memory and CPU that we could get on the Dell are 910. So in this specific setup, again, you can get the details in the white paper, but we were running two different test setups. The blue line here shows us running a test generator against a test target running on the same hardware. So basically, if I recall correctly, probably this was web testing, so it was running HTTP test generators against an Apache open source web server. And of course, you can imagine that you can realize that they are actually sharing the same CPU resources and memory resources. Running similar hardware setups, but having test generator on a separate hardware and the target on a different hardware immediately doubled the test efficiency. And at some point, you met a bottleneck, and the efficiency didn't increase that fast anymore. And here you can see that we actually have 15 parallel processes running, and I think it was in two-threaded mode. So there was some sharing of the memory resources used in this setup. But here again, the main point is understanding that the architecture that you do in your tests, if you run your test targets on a virtual host on the same computer, then you are not going to reach the same load as with having the test target on a separate hardware platform, and that platform also needs to be high-end hardware. As you can see, the CPU usage of the Apache web server itself and the test generators were about equally the same. So so half of the CPU and memory from the hardware was used by Apache, and half of it was used by the test generators.